So the mechanical problem of interest of this talk is the one that you can see here. I've been already presenting the experimental results in the previous series of these conferences, and experimental results are also already published in a number of the IGF journal, therefore you can find further detail there. However, the experimental, the coating I'm referring to is actually consists of this layer of corrosion products that one can find inside pipelines, in this case for oil transportation. This same product that you see here, covered by a layer of dry oil, can also be produced in laboratory in order to understand what is the influence of the production process on the chemistry. As you likely know better than I do, so these corrosion layers are made by the interaction of ferrous ions with carbon dioxide and water, which usually are transported together with the hydrocarbon. And this reaction produces iron carbonates, which precipitates in the form of scales on the surface of the steel. And the beneficial effect of this layer is that it prevents iron from further dissolution, and therefore it has an interesting protection effect. So the morphology and the size of the scale depends very much on several factors. Here we see two examples of these. What is known is that usually these products are for compact layers on the surface of the steel with a high protective characteristic. And nevertheless, it is also known that due to some accidental action, you might have detaching of this coating from the substrate, and then the fluid flow can remove some of this particle of this scale, and this produce a very localized dangerous corrosion. The adhesion characteristic of this coating to the steel substrate can be evidenced, for instance, by indentation test. This is one of the examples of the result that one can obtain by indenting by a Rockwell tip these kind of material systems. As you can see here, the scales are removed, especially in the piling up area of the indenter imprint. So the image is more clear here. This is the shape of the conical tip of the imprint, which is on the steel substrate. The effect of these scales is also reflected by the indentation curves. The black curve here refer to the plain steel, while these other curves refer to this combined material system. As I was saying before, the interaction between the process and the material can produce scales which might have different properties. Here we see another kind of, again, iron carbonate. In this case, as you can see, the corrosion has progressed beyond the coating layer. There is a clear diffuse fracturing on the substrate, and these cracks are also evidenced by these kinks that we can notice on the indentation curves, which were not present earlier. The test can give some insight on the characteristics of the coatings. Nevertheless, we tried to get a better understanding of the mechanism which underlies this kind of failure by some simulation model. We can perform a quite reliable simulation of indentation test on steels, on metals in particular, using classical model like HAM model. What we see here is, for instance, the comparison of the geometry of the imprint, which has been obtained experimentally and which has been calculated by finite element models. In this material system, then the substrate is well characterized and well modeled, and we focus our attention on the simulation of the coating. In the initial phase, we are using finite element models And for this coating, which also presents some brittleness, we were using a interactive Fragment plasticity model with a phenomenological model with describe the damaging processes. So what one can see using this kind of analysis that we can reproduce the main feature, for example, what concerns the force displacement depth. Also in this case, the outer curve is the one which concerns the damage model, and then depending on the characteristic of the coating, you can have different responses, similar to the experimental one. We can easily single out that the most damage occurs in correspondence of the piling up area of the imprint, which is consistent with experimental observation. And here we see some damage, compression damage model due to the interaction with the indenter. And in this case, this is rather a shear induced damage. We can also represent the prevailing shearing mode that occurs at the interface between the coating and the substrate. If you look carefully here, there is also some opening, but it's quite difficult to go beyond this kind of analysis, even introducing cohesive surface in this kind of models. Therefore, with a master student of mine, which is the code of this presentation, we try to use a completely different approach, which is based on the discrete element method. So in this case, the model, so the mechanical model is much simple in the sense that there are no material nonlinearities. There are no large Planck strains, which are important for representing correctly the formation of the bulk materials. Rather, most nonlinear phenomena are concentrated at the interface between the elements. In several cases, these elements are just considered rigid bodies, but in this coupled FEM-DEM approach, which comes from this professor at Queen Mary University, so all these triangular particles are also considered as elastic models. The strains are small, but we can admit a very large displacement, as we will see. The main mechanical limitation of this approach is that the code that we are using can implement either plane stress element, which is what I'm going to present, or quite consuming 3D elements, which we didn't approach yet. So in this case, as I was saying, everything here is elastic. All inelastic effects are at the interfaces of all the elements, both in the coating and the support. And the interface response is of this kind, in which we have, let's say, an initial reversible part, which depends on these parameters, which is a key parameters of the simulation. And then we have a quite, let's say, traditional linear softening when the material is going to fracture. So the parameters that we implemented are the same of the finite element model for what concerns the elastic response. We were given different interface properties to the bulk material, the substrate, which was not supposed to break, and to the coating based on some data that we can find in the literature. So the results from a qualitative point of view are quite interesting. In the sense, here you see again some of the experimental results that I quoted already. And as you can see, when the indentation test produces detachment of the coating from the substrate in maybe different layers, and also by quite long distance from the axis of the indenter. And this kind of phenomenon is also captured by this FEM-DEM approach. These red lines are the interface along which some sliding is going to occur. And if we look at this kind of details, then we can also see that there is some opening, which is consistent also with the result of the finite element model, despite the completely different theory which is behind this analysis. If we proceed further, then we clearly see that this approach actually permitted to represent the fragmentation phenomena that we see in the experiments. Again, the material tends to crack in correspondence of the piling up area. What we can see is that also the deformation of the bulk material is quite realistic, despite the fact that there is no plaster deformation here, but rather most deformation in this part is likely reproduced by this, let's say, interface behavior. In this case, we can also see there is a crack which is going to propagate. The problem, as I was saying, is quite sensitive to parameters, and we just show you how the results change if we assume that this initial hardening phase of the interface is very small, consistent with typical brittle fracture phenomena. And then, as you can see, the results are quite different from the experiment. Still clear there is the sliding across this interface, but this the failure mode of this system, as you can realize from this picture, is much more brittle than it is in practice. So, concluding this feasibility study, what we could see is that, well, this kind of couple finite element, discrete element approaches seem suitable for this, for approaching this kind of problem. Again, taking into account that the substrate in this case, the substrate in this case is mainly important mainly to confirm the proper compliance of the system. We obtained quite satisfactory results in qualitative terms, which we are not able to get anyhow from more sophisticated finite element approaches. Here there are several improvements which are required for getting also quantitative comparison from this test, but this is still research which is ongoing. Maybe next time I will be able to show you some further results. Thank you very much for listening.